This example comes out of section 10.1, the beginnings of chapter 10, function operations. This is about sums and differences of functions. So in this first example, we're given a couple of functions here. G of x equals x squared, and f of x equals 9 plus 6x. Hopefully you have some sense of what those two functions themselves would look like. In fact, we're asked to draw them in a moment anyway, so I might as well take a second and say, okay, well I know that g of x equals x squared looks something like this. And f of x equals 9 plus 6x is going to be, a straight line function, relatively steep slope, something roughly like that, without doing too much labeling. That's f, and that's g. The equation of h of x equals f plus g of x is the same thing, by the way, as f of x plus g of x, and so you're really just being asked to add these two things together. So my new function is now going to be 9 plus 6x plus x squared, which more commonly we probably would write as x squared plus 6x plus 9, and you could even write that as x plus 3 in brackets squared, since it happens to factor nicely, which will help us in a minute when we do go to graph this thing. So sketching f, g, and h on the same set of axes, we've already got f and g. H is going to be this parabola now that's just been moved 3 to the left, so something like this. And we've got a parabola facing upward. It's not immediately obvious how the two f and g added together to give this h, but we'll address that down below. Now we can talk about the domain and range of h of x. The domain is just x can be an element of all real numbers. There's no limit on what x can't be when you've got a parabola y equals x plus 3 squared. The range, however, is a little bit limited. You've got y needs to be greater or equal to 0. There's no negative values once you square the x plus 3. So you've got that as your range. Now, the table here is maybe a good introductory way of looking at these sum functions. Like if I put in 0 into the regular f of x function, I get a value of 9. If I put in 1 into f of x, I get 9 plus 6, which is 15. If I put in 2, I get 9 plus 12, which is 21. And if I put in a negative number, 9 plus negative 6 is 3. Those points themselves not particularly interesting. You connect the dots and you get a straight line that has a slope of 6 and a y-intercept of 9. Now g of x, again, is by itself just a plain old parabola that we see many times before. 0 squared is 0, 1 squared is 1, 2 squared is 4, negative 1 squared is 1. H of x is just the sum of those two things. So 9 plus 0 is 9, 15 plus 1 is 16, 21 plus 4 is 25, 3 plus 1 is 4. And again, plotting these points, if we had a big piece of graph paper, you might be actually surprised to discover that they fall on the parabola of y equals x plus 3 squared. But just an interesting way of looking at functions, adding them up. Notice that it wouldn't have mattered if I would have made up a new function called m of x and said it's g plus f, because we're adding g plus f is equal to f plus g, so it wouldn't have made any difference to this question whatsoever, which is different than when we start to do the difference functions where we're saying f minus g or g minus f, where they would normally be two different pictures, two different functions.